let's indeed check. Yes.
Okay, so we have more and more people connecting, so you will have the audience. Very good.
Yes.
Can I say something? Alexei, your talk was very good yesterday.
Oh yeah. I enjoyed it as well. Yeah. Congratulations. Yeah, very good. Yeah. Yeah, we can see your screen.
Yes. I'll put it in full screen.
Yes, we can see the full screen.
Perfect.
We can hear you. Okay, so let me give another 2 or 3 minutes. Okay.
Yeah, sure. Yes.
Good morning, everyone.
So you see my screen, you see my pointer, right?
Yes. Yeah.
Okay, so I'm ready then. Yes.
Yeah, you're ready. Yeah.
Bonjour.
Okay, I think we have already an audience, so we can start our morning session. And it's my pleasure to announce a talk of Nika Akapian, which is entitled Multi-Qubit Photonic Devices Based on Crystal Phase Quantum Dots in Nanowires. Nika, please.
Thank you, Vladimir. It's a great pleasure to be here. It's thank you for the opportunity and the invitation to give a talk. It's always a pleasure. So good morning. I am Nika Akapian from DTU, Technical University of Denmark, and today I will describe our multi-qubit project funded by a recent ERC grant. So the key goal here is to create multi-qubit photonic devices. A strong potential that such devices may be a prototype of the forthcoming quantum internet. However, there's a challenge. a technological platform to make such devices does not yet exist. So before we start, just to make a general background for all of us. So what do we expect from the quantum internet? In general, at least two key functionalities: send and receive quantum information, and to connect quantum computers across the network. So every node in such a network needs to be able to send, receive, and connect qubits. And then, what is the key element of such a node? It's obviously it's a multi-qubit device with a photonic interface. And we might ask why multi-qubit and why photonic? And the need for photonic part, I think it's very clear. It's photonics. It's the only way for now to send information over long distances. The multi-qubit part, it's probably also clear, right? To have real advantage, we need multi-qubit system. It's very similar to quantum computer, right? To have real advantage, we need multi-qubit quantum computers with multi-qubits. So what do we need now to make such multi-qubit devices? Well, multi-qubit devices without photonic interface are already existing today. We have multi-qubit quantum computers, for instance, from Google or from IBM. And excellent, on the other hand, excellent quantum photonic devices also exist. But the solid-state platform is not a multi-qubit device. For instance, today we have single photon sources based on quantum dots, NV centers in diamonds, and several others. But what we need, it's a combination of both multi-qubit solid-state device and a photonic interface. Again, as I mentioned before, there is a challenge. The technological platform to make such a thing does not yet exist, right? So, there are several limitations. The first technological challenge is a material platform. So what we want, as I mentioned already several times, a multi-qubit, multiple solid-state qubits here, all connected quantum mechanically, for instance, entangled, and a flying photon. Right, the goal of this flying photon, it will also be entangled with this qubit, and it will carry quantum information from one node to another node in a system. Right now, quantum dots are perhaps one of the most promising candidates for such a system because they have already built-in quantum interface between an electron and the flying photon, right? So electron is the solid state part, and the flying photon will be obviously the photonic part. So in principle, quantum dots can also be designed the way we want. For instance, we know that we can grow them in different sizes and engineer them such that they emit photons at different frequencies. And also, in principle, they can be scaled. Right, so multiple quantum dots can, in principle, be grown, forming a single multi-qubit quantum system. However, in reality, the field, unfortunately, has not advanced beyond the two coupled quantum dots as shown in this picture, and that only few groups have demonstrated that. So what we have is that no two photons are the same, no advancement beyond 2 qubits, and no way to realize a multi-qubit system in solid state, especially when we want to keep the design flexible and benefit from an optical interface. Now, we all might ask, why is that? And it seems to be a material problem, in a way, a fundamental how quantum dots are formed, right? So the conventional quantum dots are small bandgap semiconductors surrounded by a large bandgap semiconductor. So one material surrounded by another material. And even if we try to make perfect shape, we know that there is always interface between the two materials, and one material can always diffuse into another. Again, even if we try to make in the beginning a perfect interface. So this diffusion will usually smears the interface, and we see this blurred interface like in the picture here. So clearly, one of the challenges is to make quantum dots the way we want, exactly the way we want, with almost perfect structuring. And we have a solution. And I'll describe in later slide. But then, what is that we want from such structures? We want an ultimate precision during and also after the growth, right? What we want that all quantum dots, which are shown here, and it will be nanowire, are the same or different. And if they're different by our design, so here all quantum dots on purpose different, again different by our design, such that different size will give different energy confinement levels for electrons and holes, and therefore they can be individually optically addressed, right? And to do this, we also require a perfect accuracy. So ideally, we want to control each quantum dot with the ultimate accuracy of a single atomic layer. But there is more to that. Even if we can make such an ideal structure, then there are other questions. How do we load charges like here exactly in places that we want? Right, has to be fast and reliable. And then, if we load these charges, how do we connect them all quantum mechanically? And once we, let's say, solve that problem and connect them quantum mechanically, how do we send this photon out such that it's entangled with all this multi-qubit solid state system? So here we have to develop new concepts for all these three parts that do not exist yet. Model them numerically and eventually realize experimentally. And we do have some of our first results. So our basic structure for study devices is a crystal phase quantum dots, which is schematically shown here, and one of the example of grown structures is shown here. So we collaborate with group of Jean-Christophe Armand and Federico Panchera in Paris in C2N, and we get these beautiful samples from them, where they indeed learn and know how to precisely control such a word-side Ziegler crystal phase structure with a single atomic layer. So and the advantage of this crystal phase quantum dot is because they made of the same material, right? For instance, gallium arsenide, but different crystal structure, and this cubic or hexagonal word-side or Ziegler, right? And the key point that the crystal structures do not intermix. Unlike here, you can have diffusion from one layer to another. Here, crystal structure do not intermix. So interface is always atomically sharp. If you create like this, it stays like this. So now we can make quantum structures with ultimate accuracy of a single atomic layer, as you can see here. So this is again high resolution TM. Each line is a single atomic layer of word-side or Ziegler structures in gallium arsenide nanowire. So quantum dots are formed by confining electrons in the conduction bands and holes in the valence bands. As you can notice here, this is the conduction band, this is the valence band, this is the word-side part, and this is the Ziegler part. If we make sizes of word-side and Ziegler part short enough, then we can have confined level for electrons in the conduction bands and holes in the valence band. This is an example when we schematically design these two quantum dots for electrons to be a little bit different by size, or quantization levels or confinement levels for electrons here in the left quantum dot and in the right quantum dot will be a little bit different. So these are two individually addressable quantum dots. Notice that electrons and hole form type 2 band alignment. And this is very, very crucial, because this hole allows us to connect two electrons which otherwise are individual. We can separate these two far from each other, such as the wave function of this electron doesn't overlap with the wave function of this electron. So in principle, quantum dot in the left electron in the quantum dot in the left does not talk with electron in the quantum dot in the right until we introduce this hole. Once we introduce this hole here, the wave function of the hole will overlap with the wave function of the electron in the left dot, and with the electron and the wave function of the same hole will overlap with the wave function of the electron in the right dot. And this overlap and this hole actually can connect to quantum. And this is crucial for us in order to, as you will see later, initialize charges and also connect them quantum mechanically. So I will show our few concepts. Now, in this video, perhaps you've seen already by previous talks, so shows how our collaborators at C2N can grow and control layer by layer such a structure. So you see a real-time image of high resolution, real-time video of high resolution TM. Again, showing layer by layer growth of such structures. And by changing growth parameters, it's possible to control which structures in nanowire will grow, to word side or the ingredient. So now, once we know how to make such structures, right? We want to define the we want to make quantum mechanical operations, right? So the first thing is, what is our qubit? And here we introduce a new type of qubit, which is called location qubit. We call it location qubit, and it has several advantages. It's not yet just another qubit that we add to the family, but that's a qubit that uses advantages of our system and has some better coherence properties, which I'll talk in a bit. So for qubit, we need to define what is a zero state and what is a one state. So now we have two crystal phase quantum dots for electrons. So when electron is on the left dot, it's our zero state. When electron is on the right dot, it's our one state. Still, I don't tell you, not describing how we create electrons, how we move them here, but let's say if we can put one here, it's a zero state. If we can put one here, it's one state. But now if we can make a superposition of this electron to be at the same time in the left dot and in the right dot, then it's a superposition of 0 plus 1 state. Note, these are not two electrons, one here and one here. It's a single electron, but it takes it's in superposition of single electron in a superposition of two locations, left location, right location. So it's here and here at the same time, and it's from 0 plus 1 state on the Bloch sphere. So because we manipulate with locations, left and right is location, we call it a location qubit. Now, in order to move electron from 0 state to 1 state, or create from 0 state 0 plus 1 state, we have to know how to do it, right? And we adopt the concept from similar to what people do in atomic physics. It's called detuned stirrup. So with two lasers applying to these two levels, we can perform all single qubit gates, which are Pauli X, H, and T. Essentially, these gates are rotation of a quantum state on the Bloch sphere, right? This is the Bloch sphere. It represents all possible states that qubit can be in. The North Pole is a 0 state. The South Pole is 1 state. Any state in the equatorial plate, it's a 0 plus 1 superposition with different phase between 0 and 1. And any other states, it's just other combinations of 0 plus 1, right? So in order to make, let's say, move it from one state to another, in Bloch sphere defined as rotations around the axis. So you have to define the rotation axis. Let's say it's this blue arrow, and then to perform a rotation around that axis. And in very general, from initial state I to the final state F, it will be rotation by an angle gamma around this axis. So if we can, in our system, define these three angles of the Bloch sphere, alpha and beta and gamma, we can make any rotation. So alpha and beta are the two angles that define the rotation axis, axis, and angle gamma defines how much we rotate around this axis to move from any initial state to a final state. So clearly, depending how we put the axis, we can make any rotations. If the axis is in this direction, we can rotate from 0 to 1. So how to do it? So the concept is called stirrup, actually detuned stirrup. It's a smart application of two laser pulses which are detuned between ground state and excited state. So what is the ground state? A ground state if when we have an electron in the left dot or electron in the right in the right dot. An excited state if we have created while we have one electron, we have created another electron hole pair here. So it's you can see it has 2 electrons and 1 hole. It's a negatively charged exciton, right? Usual exciton is just electron and hole pair. If we add the extra electron, it has negative charge because there are 2 electrons, so it's negatively charged electron. So if we simply come with the energy difference between these 2 levels, we will just excite the exciton, which can decay radiatively. But that's not what we do. We apply 2 lasers again in a smart way, detuned from this negatively charged electron transition, and if it applies them at the same time and carefully choose the detuning and a phase between these 2 detuned lasers, we can define all these alpha, beta, gamma angles in this Bloch sphere, and eventually perform all single qubit gates. So we can create any superposition of any single qubit state on the Bloch sphere of this location qubit. So far we have created the concept, and we also modeled the concept to see is it actually good. And one of the things is one of the characteristics is what are the gate fidelities. It's how sure we are that gating operation that we want to perform it will happen. And another key parameter is coherence time of our qubit. Right, so gate fidelity, as you can see, those are 3 modeled calculated gate fidelities for Pauli X, Adama, and another phase, T phase qubit. They're all above 99 and a couple of nines after the point. So it's very potentially very good. And of course, we modeled for ideal case and for realistic case. And in realistic case, we included all possible decoherence mechanisms, such as charge fluctuations around the system and phonon-based dephasing. And of course, in realistic cases, gates are a little less accurate, but still very close to ideal and beyond 99, and in this case, all of them 99 and 2 nines after the point. So it's all very good so far. And another important things, it's a qubit coherence. So qubit coherence is maybe one of the crucial things in qubit. It tells how long we keep quantum information encoded in our qubit, right? At some point it will decay and we will lose it, but while it's there, we can make our quantum computing operations, right? And here comes another advantage of this location qubit. So it's we predict from our realistic models that at 1 Kelvin it can have 1 second coherence time, and maybe 1 Kelvin is it's nowadays reachable temperatures, and obviously it scales with temperature, but you can really reach high coherent times at achievable temperatures, cryogenic temperatures that we have today. And why is that? because here one of the advantages that we do not use spin of the electron. Perhaps many of you know that one of the well-known qubits, it's electron spin qubit, where quantum information encoded in superposition of spins, spin up and spin down. That's of course a very good qubit, easy to operate, couples nicely to polarization of light. However, it has this decoherence mechanism which are intrinsic to our semiconductor system. There are fluctuations of a magnetic field coming from a nuclei, and that's the main source of decoherence of a spin qubit. Now here we do not have spin, so we do not have any fluctuations actually we do not use spin as a part of the qubit, and we do not have any fluctuations of fluctuations of magnetic field of nuclear do not affect the coherence time, and that's why decoherence coming from a random magnetic field is not part of the game, and that's why we have expected longer coherence time. Now, a super concise introduction to quantum gates. So if we want to make multi-qubit devices, we need to make any kind of quantum computations there, and typically if one can design and demonstrate a universal set of gates, then any quantum computation operation can be done. And there are many equivalent universal set of gates, but we just choose a common set. Common set consists of this four gates. So 3 single qubit gates, Hadamard phase and T, and one 2-qubit gate, which is CNOT gate. So Hadamard gate, it creates a superposition. If you've been in state 0, it can bring you to superposition of 0 plus 1. There are 2 phase gates, S and T. They simply add phase. Let's say if we are in superposition of 0 plus 1 with 0 phase, then this S gate can give us phase I. If we are in superposition of 0 plus 1, the T gates can give us a phase pi over 4. So this marks with these 3 gates, we can make any rotation on a Bloch sphere for a single qubit gate. So far, in the previous slides here, I showed that we can make and simulate and model all this single qubit gate. And if we want to connect 2 quantum dots, see, if you want to make a connection like this between one dot and another dot, and connect them quantum mechanically, we need 2-qubit gate. And one of the 2-qubit gates, let me come back, is a CNOT gate, right? The CNOT gate, simply saying it creates entanglement. So if together with Hadamard gate, if you apply it on 2 qubits, on 2 individual qubits, it can entangle those. So, and here comes our way how we implement a 2-qubit gate in our system. So here I have a qubit 1, which is control qubit. So this is these are 2 sides for qubit 1, and this is a control side, which is not part of the qubit, but it's part of the control. And these two quantum dots are our target qubit. Now we know that we can move electron in our target qubit from left dot to the right dot. Let's say from here to here. Now we want to perform this movement only when this electron is here. Remember, when this electron is here, everything which is there feels Coulomb potential because they are close, and Coulomb interaction means that the energy levels that we apply to the system to move electron from here to here are different, where this electron is here or not here, because it will be different Coulomb interaction here and different, and it will slightly change the energies. So we prepare our operation from moving this electron from here to here in a situation when the electron in the control dot is in the control side here. So now, if this electron is not here, our operation will not do anything. But if the electron is here, then our operation will actually work, because now lasers will be aligned with the system and will move eventually electron from here to here. So this is our scheme how to make a CNOT gate which entangles the qubit. So step 1 is to enable control, means to move this electron from here to here. Step 2 is perform not operation, which means move this electron in our target qubit from left to right while this is here. And step 3 is disable control, so move this electron back from our control side to the previous location. So, and eventually by doing this, we can flip from 0 to 1 our target qubit when control side is on. So this just shows a population during each level and each state during our gating time. And this is a fidelity of operation, fidelity of flipping or moving this electron from on the target from here to here. Again, fidelities are above 99.9%, and the time scale for this is actually picosecond. So we can make all our gates single qubit and multi-qubit and 2-qubit on picosecond time scale, which is actually fast. So now all this scheme assumes if we can initially load electrons on the sides the way we want, but it's also not known. So for instance, how do we load? If you look at this again, this is the nanowire with multiple crystal phase quantum dots. How do we load electrons on the sides the way we want? And again, here we use our built-in type 2 transition. We use the fact that this hole can connect these two otherwise remote electrons. So in our scheme, we have a charging region in the middle, a hole region in the left, and an electron region in the right. So charging region is solely to create an electron hole pair. So here we create an electron hole pair. Then we move electrons away to an electron region and move holes to a holes region. So holes we completely discard them. We don't need them. They're just in the buffer. But this way, and in the next slide, I'll explain how exactly we are doing it. This is just step 1, step 2, and step 3. So we can create electrons all optically in quantum dots exactly where we want, also with high fidelities. So now, how do we do it? So this scheme describes the part of charging region here where we create charges controllably. So it's very simple. What we do, it's you can think it is initialization of electrons by waiting. But you don't only wait, you excite this dot with a laser, resonant laser that can excite this electron hole pair. And in this pair, you come with another laser tuned to these resonances, and you excite it with this electron hole pair. So you come with 2 layers at the same time, and you create this exciton and this exciton. So what can happen now? If you have created this electron hole pair, it can recombine back and give you a photon back. This can also recombine back and give you a photon back. These are one of the possibilities. However, there is also another possibility that this electron will recombine with this hole, which is shown here. And if this will happen, we are left with an electron on the right side here and hole from the right here. So now they're separated a lot, and their wave functions do not overlap very, very little. So essentially, this is a very stable electron. So this and will not recombine radiatively. So by what it means, by shining with 2 lasers and waiting until this electron hole pair will recombine, we create such a state. We have a stable electron and stable hole. So what's left now to move this electron further into the electron state, into the place where we keep the electrons, and the hole to the place where we keep the holes. Perhaps I don't have a lot of time to describe details of the schematics, but I think I described you the concept. So all optically coming with 2 lasers and waiting until this will recombine, we can create electrons the way we want. Of course, we simulate the result, and this is our pumping time, and this is a charge initialization fidelity. So, and we can see that we can reach again way above 99% of creating charges in our system if we wait a few microseconds. Clearly, more we wait, more sure we are, but at some point it saturates. This is a simulation of realistic system that we can grow, and we can see that after 4 microseconds we are essentially able to create electron hole pair. Now we can also increase fidelities if we want of our charge initialization simply by increasing the length of our structure. Why is that? Because when we increase the length of our structure, so wave functions of electron holes are more confined, and the overlap is smaller. And smaller the overlap, less unwanted recombination that we want. So by increasing the structure, we decrease the overlap and increase our fidelities. Of course, because of overlap of electron hole is now smaller, it affects timing of the operation. So we have to wait for more time. And clearly, if you want higher fidelities, that is shown in this curve, in the red one, you have to wait longer, which showed in this blue curve. And this is our sweet spot so far. If we wait for 4 microseconds, we can have fidelities 99.9, which is shown here. Now, when I described how to create electron and hole, we also need to know how to move these electrons the way we want, right? And it's also in a very similar scheme. Let's say we have electron here in the left dot. Now we want to move it to the right dot, and then by repeating the scheme, creating electrons and moving them to where we want, we can charge or initialize electrons in our crystal phase quantum dot exactly the way we want. So how do we do it? There is a coherent way and incoherent way. Incoherent way is very simple. So we have this electron here, and what we do, we simply excite this electron hole pair. So what can happen? We excite this one, okay, this can recombine back and nothing happens, so electron left here. But when you excite this one, also this pair can recombine. And when this pair recombines radiatively, photon is going out, and then you left with electron on the right side. So simply by exciting this transition, you can and again, by waiting, you can move, you can destroy electron on the left side and create electron in the right side. That's why we call it incoherence. We create one and destroying another one. And again, this is the waiting time that you need, and the blue line shows you a fidelity of incoherent electron transfer, all optical, between left dot and the right dot. And again, with so this time is not in microseconds, but the time scales here are also microseconds, because dynamics is the same as before, and we can reach very high fidelities. But sometimes you want coherent transfer. You don't want to create electron here by destroying electrons there. We want to adiabatically slowly move it from one side to another. In this case, you can apply stirrup scheme. So you come with 2 lasers. You actually do not create an exciton, but you are I don't describe details, but it's well-known stirrup scheme, stimulated Raman adiabatic transfer, well-known in atomic physics. We apply it here with 2 lasers, and then we can move electron from here to here coherently. It's the same electron that was here. Now it's created here, and the times for the coherence transfer are also very similar, as shown here with this red curve. Okay. So we not only want to create such electron, but also want to verify that the creation has been done successfully. How to do it? This is our proposal how we will experimentally verify it here. So usually in experiments you don't know the exact transition of this exciton in exact transition of this exciton. What we do in experiment, we scan the laser around this transition and find resonance, and scan the laser around this transition and find the laser and find the resonance. And when both lasers are in resonance, one here and one there, then the magic will happen. Then we can wait until this recombination will happen and create an electron here and hole here. And that's what's shown here. It's a detuning of the laser A, detuning of the laser B. When detuning is 0, it means we are exactly in resonance. When detuning of laser B is also 0, it means exactly we are also in resonance. And when we are in resonance, of course, when we expect to create our electron here. However, when we create it like this, we cannot measure, because this electron hole pair does not recombine. So we need a way to know if we successfully created such a pair. And the way experimentally verified, it's actually to monitor this transition all the time. Because if we created this electron, we cannot excite it anymore. And this is what's shown here. So it's again, we scan laser A, and 0 is 0 detuning, so it's resonant with the level here. And again, the scan laser B, the same as here. But now what we monitor the fluorescence from here. And if we have created successfully this state, then we cannot anymore excite electron hole pair here, and fluorescence will be 0. So this will be experimental measurement of detuning from laser A and detuning from laser B, and measuring exciton A fluorescence intensity. And if we have here, then we have created an electron and a hole in two remote quantum dots, and they are stable. Well, all this requires resonant excitation. And resonant excitation with quantum dots is already a well-known technique. However, so far it has not been done and demonstrated until recently with nanowires. Why is that? Because resonant means you come with a laser to a transition of where you have a single photon emission. And laser has usually billions of photons, and a single photon emitter emits only one. So if they have the same energy, what you want to somehow distinguish this one single photon out of the same type of photons, but which are billion times of more. So how to do it? So people use it with cross polarization excitation. So the excitation of the laser has one polarization, and the emitted photon have a different polarization. And by distinguishing the polarization, if you do it carefully enough, you can distinguish this single photon from the laser, from the reflected laser. So what's the problem with nanowires? With S-grown samples, the problem is actually not the nanowire, but the surface. You see, the surface is always rough, and it means it will change the polarization of the laser. So if you come with a certain polarization and you want to distinguish, after reflection, it will be actually not as good. So that's why that's a challenge here. But what we have shown that it's in principle, not in principle, it's actually possible. So if again, by carefully doing this, surface also degrades your rejection quality, but it's still possible. And that's our setup. Nanowires are here, objective here. That's a polarizing beam splitter. Laser comes with one polarization and excites a nanowire quantum dots, and emission from another polarization goes and collected here. So we are able to perform resonant fluorescence. This is an example of scanning a laser through a transition of an exciton in a quantum dot in a nanowire. Here is an example of two photon excitation. So we can come with a laser in between exciton line and the biexciton line. So this is the exciton line, this is the biexciton line, and this is the laser. So when laser is in between, you can have two photon absorption. So two photons from the laser have exactly the same energy as the biexciton, and then you can have a cascading emission from the biexciton to the exciton and to the ground state. How much time do I have? Is it 3 minutes left, Vladimir?
Yeah, you have 5 minutes, no problem.
5 minutes, no problem. Okay.
Yeah.
Thank you. So let's say we know how to make our single node in a quantum network, right? It's a multi-qubit device with a photonic interface. It's based on crystal phasors and nanowires. We know how to excite resonantly, and now we want to send one information from one node to another one. So what's the next problem? The next problem: these two nodes have to speak the same language. So in our case, have to exchange photons of the same frequency, right? And but even if we do different quantum dots, the same quantum dots, and put them in different locations, then unlikely they will have photons exchange photons of the same frequency, because something is always different. Magnetic field is different. Electrostatic environment is different. Something. There are many reasons to affect the emission of the dot. So what we want to do, we want to ensure that two nodes, all the other nodes actually exchange photons of the same frequency. And we borrow the idea from GPS satellites in atomic clocks. All satellites are synchronized to the same frequency of atomic clock, and we can use the same. So each quantum dot will be frequency tuned and locked to atomic transition. This is our quantum dot, this is our atom, and in our case, if quantum dots are gallium arsenide, then atomic transition of rubidium atom, it's the same frequency, so we can tune and frequency lock each node to the same atomic transition of rubidium atom. So all the quantum dots in this node will emit exactly as rubidium atom tells them, 7-8 nanometers. Here, every time it's the same, right? Visually, it's like in music, you have all your quantum dots and you bring them, frequency tune them, and then lock them to the same transition of rubidium, right? And then you can apply also feedback and to ensure that the tuning is always there. That's schematically what it is. So why it works? Because gallium arsenide quantum dots and also in nanowires can be designed to emit at the wavelengths of rubidium atoms. So this is our quantum dots. We can design them by choosing a proper site to emit around 7-8 nanometers. And 7-8 nanometers, it's exactly the ground to state transition in rubidium atom here, right? So and the experiment is that's one of the original experiments. So we have a quantum dot. We tune the emission frequency with magnetic field, right? Here we change magnetic field. The color shows intensity, and as we apply magnetic field, then levels of the quantum dot follow Zeeman split and diamagnetic shift, so that we change the energy. And once they are in resonance with rubidium, we can see that every time it's resonance, the photon coming emitted from the quantum dot are absorbed by these rubidium atoms, and therefore are not detected by detector. So these missing peaks are missing photons which were absorbed here. So this shows that that's again one of our very first experiments. We can frequency tune emission of the quantum dot to the exact transitions of rubidium. So, and of course, we did the same with nanowire quantum dots. So here we tune the quantum dots in nanowire, gallium arsenide quantum dots in aluminum gallium arsenide nanowire. The samples here grown in the group of George Silin in St. Petersburg Academic University. You've heard the talks from the group also here in this workshop, and this is the result. Here we change magnetic field from 0 to -1 Tesla, here from 0 to +1 Tesla, and here and here this line is undergoes Zeeman split, and when it couples, when the energy is exactly matches the fine-tuned transition of rubidium atom, we see absorption. So in fact, we also know that nanowire quantum dots can be tuned and also locked to atomic transitions. And this is my visionary summary of our goals of what we want to do. So the key message is we are on the way to creating a multi-qubit device with a photonic interface, and hopefully it can be one of the key elements of the quantum dot of a quantum node in a quantum network, where multiple qubits in different nodes in the network can be exchanged with via photonic interface. Hopefully it will work, and it's crucial for several applications in quantum technology. For instance, where devices with multiple quantum bits are vital, like in quantum internet. And thank you very much for your attention.
Thank you, Nika, for the nice talk. Are there any questions? Frank.
You are muted, Frank.
Two questions about the geometrical control of these crystal phase quantum dots. Do you use confinement only along the axis, or do you also need confinement in the lateral direction?
Yeah, well, we need both, and such a structure actually will work. So typically here you have just few nanometers, and here maybe 20, 30 nanometers, maybe 40 nanometers is enough.
Do you need to control the radius of the nanowire also within one monolayer?
Preferably not. Well, of course, if there are fluctuations on the lateral dimension, it will also change a little bit. But the key change comes from adding or removing a single layer in this direction, because it's smallest direction in the quantization. If you change by one layer here, that's the main change will come. Of course, fluctuations here will also affect, but it will be minor compared to here, right? So our preference would be to have, of course, as diameter as the same as possible. And if there are any fluctuations in this or change in diameter, so we will see them in spectral characterization of our quantum dots. But the control will come from changing the size of layers, number of layers here. Was that?
Yeah, that's clear. Yes. Second question. I guess the device will contain several such nanowires. Is it right?
So device is just one nanowire. But
one nanowire.
One nanowire, but many dots.
So there's no question of uniformity of the thicknesses of the crystal phase between different nanowires. This is not not an issue.
So many experimental questions we still don't have the answers, right? Because the experimental part is in the very beginning here, right? So far we worked on randomly formed crystal phase quantum dots, again coming from Jean-Christophe, and right, and from then we know there are single photon source emitters, but now with this new machine you have there, we will our goal is to have just one nanowire grown just for the product, right? The one that will be absorbed by the TM, and where each quantum dot, each crystal phase section will be grown by exact design that our numerical model tells, in order to to make this different dots by different design, right? So we need just, of course, millions are growing around, but we need just that one grown for this. So one wire, one device.
All right, thank you.
Alexei?
Thank you for such inspiring talk. Am I correct that every quantum dot in a multi-qubit nanowire should have our own size and bandgap in order that we could control electrons selectively in each particular bin? I just think about that if we add here different energy states depending on neighboring bins, it seems the number of lasers we need grows very fast with number of qubits. Is it correct?
Yeah, absolutely correct. Yes. So of course we want each quantum dot to be individually addressable with the lasers. That's why we use the ability to grow them with different size. Different size, as you correctly understood, will give different energy level, right? And that will require different lasers to control the dot. Yeah, so conceptually, that's what we want. In practice, we have to see how exactly we are going to do it, maybe with frequency combs, but indeed, if you have 10 dots, you will need at least 10 lasers, or at least 10 laser lines, right? So, you know, they can come from maybe from one laser, from frequency comb, but you need indeed 10 individual laser lines to address, which do not necessarily have to come from 10 different lasers.
Mm-hmm. Okay, thank you.
Can I ask you also, Nika, so how critical is the use of crystal phase quantum dots here compared to compositional quantum dots?
So it's absolutely
critical.
You
have shown also gas out gas, so which one is better?
So it's you know, so this is usual quantum dots, right? A small bandgap semiconductor surrounded by a large bandgap semiconductor, and typically is you know, we cannot control the shape exactly the way we want because materials intermix.
No, I mean nanowire quantum dots, like quantum dots and nanowires.
Yeah, so they are better, but still we haven't seen control like we see here. See, this is you know, if I call this ideal structure, then I have to. It's an ideal quantum dot. I don't know what better can be in terms of you know, controlling the structure. It's all atomic.
And the interface is sharper as well.
Exactly.
So
exactly, and we really count on that because you know, difference between this dot and this dot might be just single atomic layer, and this single atomic layer, based on our calculation, gives a few milli-electron volt energy separation, because you know, it's just adding one to few, it's a lot in this case, right? And so far we do not have control even with for this precise control with atomic layer, even in gallium arsenide dots and algas nanowires. Also, we know that you know from work with George and Jean-Christophe, right, that the interface is sharper there, right, because how fast the material leaves the droplet. But still, you know, I think we don't have it yet. If we have that, that's perfect. Then yet another candidate, right? Because I don't choose crystal phase just because the crystal phase, just because here we have the control. If I have control,
better control,
also
sure. I see. So I don't see any further questions, so let's thank Nika again. So, and the next talk will be given by Evelyn Gilles, and it's entitled Hydride VPE, Vapor Phase Epitaxy, the versatile and low cost process for the fast growth of 3-5 semiconductor planar heterostructures and three-dimensional nanostructures with record aspect ratio. Please, Evelyn.
Okay, do you see the screen? Is it okay?
Yes, we can see the screen,
okay.
No problem.
And do you see the laser pointer also?
Yes.
Okay,
yes.
Very good. So good morning, everyone. First of all, I wish to thank the steering committee for the invitation and the organization of this NSP conference under such, I should say, unusual circumstances. So I work at the Institut Pascal laboratory that is located in the center of France. And this laboratory is now one of the 3 labs left in the world where hydride vapor phase epitaxy, HVPE, is developed for 3-5 semiconductors with arsenic and phosphorus atoms. The second lab is Thales Research and Technology in Saclay, Paris. And the third one is Quetsch Group in the USA. And I don't know if KTH in Sweden still goes on with its HVP reactor dedicated to indium phosphide related compounds. And of course, HVP is more commonly implemented for nitride compounds, and Institut Pascal also works on nitrides. So in this talk, I would like to invite you to review the potential of the HVP technique with respect to present devices of interest, whether for the growth of planar heterostructures for shaping crystals in 3 dimensions while controlling the morphology down to the nanometer scale. And we will see that HVPE can also participate to the global understanding of epitaxial issues common to MBE and MOVPE techniques. So the results that are presented here are the fruitful collaborations, the fruit of collaboration. So it's my very pleasure to thank Vladimir Dubrovsky, Franck Glass, Jean-Christophe Armand, and Réla Pierre, as well as all members of the HVPE group of Institut Pascal and the people of the lab involved in optical studies, passivation of nanowires, or gold catalyst deposition. So HVPE was the first vapor phase epitaxial growth method, which was implemented to grow 3-5 layers and heterostructures once arsine and phosphine gas had been available. As we will see, the peculiar growth properties of HVPE are indeed borne by the chloride gaseous growth precursors as transport agents of the elements 3. And the best known HVPE property is fast growth, which is very useful to grow, let's say, metamorphic buffers, but not suited to grow thin heterostructures, which are more appropriately grown by MOVPE or MBE. Nevertheless, a few groups have continued to develop HVPE, and HVPE came back some 20 years ago when we were looking for quasi-substrates for the revival of the nitride compounds, and quite surprisingly, HVPE revealed itself to be competitive when it comes to shaping structures or crystals by selective area growth or vapor liquid solid VLS growth, including the nanometer scale with these pioneer papers about the growth of gallium nitride or indium phosphide nanowires. So in this talk, we will have a brief review of the relevant characteristics of HVPE, MOVPE, and MBE. Then we will focus on the use of volatile chloride gaseous molecules that yield very peculiar thermodynamic conditions to HVPE growth and allow to access to a kinetically limited growth regime. And the consequence of that is that the intrinsic growth anisotropy of 3,5 crystal, which is large, can be quite fully exploited to grow structures with various 3-dimensional morphologies. And the final and main part of the talk is dedicated to current HVPE realizations. So when comparing the 3 current epitaxial techniques, of course, they were all designed for condensation, but we now use them to implement solidification through VLS growth. And the main difference is that condensation is easily reversible when using chloride precursors. HVPE makes use of very high material inputs, high material fluxes, and this is something that we have to keep in mind when we will analyze the growth properties, and especially for nanowire growth by VLS, where the supersaturation of the elements will be very high in the catalyst droplets. HVPE usually implements reverse 3:5 ratios, I mean greater than 1 with respect to MOVPE or MBE. And growth temperatures are usually 100 degrees Celsius higher in HVPE for a given 3,5 material. And finally, the growth range for HVPE is large, and reactions involving chloride molecules are exothermic. So the HVPE facilities are hot wall reactors in order to avoid deposition on the walls of the reactor upstream the substrate, unlike MOVPE and MBE, where only the substrate is heated. So HVPE is commonly known as a near equilibrium growth process, and this needs to be clarified. It is known for its fast growth property, but HVP is also a process that allows to vary the condensation growth rate from 1 monolayer per second and up to 300 microns. And let's say that such a versatility is indeed often associated with the use of high supersaturation conditions, and we will discuss this assumption. So how can we read the concept of near equilibrium process from which reversible condensation results? If we look at the growth reaction of gallium arsenide, the condensation of solid gallium arsenide occurs after dechlorination and production of HCl. So please note that the arsine gas is which is introduced in the hot water reactor, is almost completely decomposed into H2, H4 molecules considered to be at equilibrium. And we will see later in this talk that when growing under undecomposed arsine, we can reach very fast growth regime. The dechlorination frequency is high enough so that there is no kinetic delay, and we observe an immediate return to equilibrium that produces the solid to an increase of the supersaturation of the vapor phase. And on decreasing the supersaturation, for instance, by the use of additional HCl in the vapor phase, reversible processes occur at the vapor-solid interface due to the volatility of the chlorides. And that is supposed to characterize a process for which the operator can really play with the reaction with respect to equilibrium. Then, a wide range of condensation rates from 3 to 60 microns per hour can be set for standard conditions, and for supersaturation ranging from 2 to more than 50. So if you look at the values of the supersaturation, HVPE, it seems that HVPE also operates at moderate or low supersaturation. So HVP is not necessarily a high supersaturation process. And indeed, we must not forget that we supersaturate with respect to a reference, which is equilibrium of the reaction, obviously. And if you want to grow, so shift the reaction towards the formation of solid, we have to supersaturate the vapor phase, which is expressed by the excess of the chemical potential that can be linked to an experimental supersaturation parameter, which is easy to calculate here from the partial pressures of the species that are introduced into the reactor and the equilibrium constant, which can be calculated from the Gibbs free energy of the reaction at equilibrium. And this one is simply calculated from the thermodynamic data related to the involved chemical elements. So written as that, a positive supersaturation means a supersaturated vapor phase, that is, there is too many reactants, so the solid is produced. And as a matter of fact, this is the Gibbs free energy difference between reactants and products for the epitaxial growth processes, HVPE, MBE, and metal organic VPE. And yes, for HVPE, the Gibbs free energy difference that maintains the stationary state between solid gallium arsenide and a vapor composed of H4, H2 and volatile gallium chloride molecules is some 450 calories per mole at 15 degrees Celsius, which indeed is about 8 times lower than thermodynamic driving force for MOVPE or MBE. Then free energy driving force ranging from 3,500 to some 7,000 calorie per mole is sufficient to promote growth in the HVP system. And this corresponds respectively to low supersaturation condition up to a medium supersaturation value. So I guess that if HVP is often seen as a high supersaturation system, it is because one may confuse with high material inputs, high material flows that are at least, and that is true, 10,000 times higher than for MBE. And another feature is to be emphasized, as with HVP is usually carried out with 3/5 ratios higher than 1, and this is of course related to the significant desorption of the volatile gallium chloride species, and that's why HVP is usually carried out with an excess of element free in the input vapor phase. So this highly reactive system needs very few material. It is supposed to be carbon free, and the hot water reactor prevents absorption of contaminants. So if you now go back to the variation of the growth rate of 3/5 EP layers with the temperature, and this variation features a growth regime limited by surface kinetics on the low temperature side, and the second one at high temperature governed by thermodynamics. Of course, thermodynamics simply foretells sublimation of the solid where the absorption of gallium chloride species does not occur anymore. And the growth regime at low temperature is very interesting because it is limited by the kinetics of each of the surface elementary steps. Absorption and desorption of molecules transporting element 3 and element 5. Then decomposition of these add molecules, and the limiting one is the chlorine decomposition and further desorption of the chlorine atom. And finally, the kinetics of the surface diffusion mechanisms. And the kinetics of these steps are different from one crystal orientation to another, resulting in different growth rates for the crystal facets. So it is possible to shape various 3D, three-dimensional morphologies by taking advantage of the fast or slow development of these facets, knowing that the growth rate can be widely varied with the temperature, as you can see here or here, or with the vapor phase. So that means that the intrinsic growth anisotropy of a crystal that is very high for the 3/5 can actually be fully exploited by HVPE to grow various aspect ratio structures in a few minutes that you can obtain by selective area growth on a masked substrate. The volatile chloride molecules do not adsorb on the dielectric film, even in condition of severe dark field pattern. Then the structures are bounded by the faces which have the lowest growth rate. It is convex growth, so a face is more developed if it grows slowly. So it's really shaping assisted by surface kinetics, and HVPE performs quite well in this field. So let's move from theory to practice with a review of realizations. So this is the direct illustration of the previous schematic drawing, and it's also a very good exercise of crystallography because this picture shows a cubic gallium arsenide stripe grown on a 1-1-1 oriented substrate, and yet not hexagonal because the opening on the substrate was aligned along the -2-1-1 direction. It is exactly what Anna von Kumberta showed yesterday for this orientation on the nanometer scale. And indeed, the possibility to exploit the high intrinsic growth anisotropy of 3/5 crystals is maintained at the nanometer scale here with the synthesis of stripes of arrays of arrays of perfect stripes presenting unusual aspect ratio in a few minutes of growth, and on a substrate which were masked with more of 90% of its area, which was masked. If someone in the audience has an idea of any use of such arrays of 3/5 stripes, please come to me. Another emblematic example of orientation controlled growth on a millimeter scale thickness is the synthesis of quasi-phase matched gratings for nonlinear optics. As a matter of fact, HVP is able to keep an original alternate orientation, 001 and opposite 00-1, all along an 8 hours groove, which is necessary to produce the half millimeter thick template suitable for parametric oscillator applications. Maybe for the young audience, these structures are used to convert a laser frequency into another by taking advantage of optical second order effect. And in order to realize the conversion, light must travel through an artificial material matrix composed of alternate 001 and 00-1 oriented 3-5 semiconductors of sufficient thickness. And the periodic inversion of orientation allows to rematch the phases of the excitation and generated lights in their travel through the matrix to overcome the destructive interferences. So let us continue with the property of fast growth. HVP has high potential to grow high efficiency 3-5 photovoltaic devices at reduced cost. At present, gallium arsenide solar cells in the planar geometry, are grown on gallium arsenide or lattice matched germanium substrates, but that yields high material and manufacturing costs that restrict these 3-5 based solar cells to, let's say, niche applications, typically space power or high concentration systems. So it is mandatory to reduce the cost of 3-5 epitaxial growth in order for these solar cells to reach larger markets. First of all, HVP replaces the expensive group 3, quite expensive group 3 metal organic precursors used in MOVP with lower cost elemental sources, and offers also conditions where growth rate as high as 3 microns per hour can be reached. And as a matter of fact, Quetch groups in the USA used a growth regime that they call hydride enhanced, which involves uncracked arsine. It's very difficult in HVP to prevent the cracking of arsine molecules unless you dramatically increase the flow rates in order to decrease the residence time of the molecules in the hot reactor. So a high hydrogen vector flow is used in the inlet tube of arsine together with a high global vector flow, typically 10 liters per minute. And this hydride enhanced growth regime becomes mass transport limited with a very high material input flows, especially arsine. And here 5/3 ratios greater than 1 are used. So growth depends mainly on the partial pressure of gallium chloride. So the question is, why do we need to work with uncracked arsine? As you can see, these solar cells, example of solar cells, needs gallium indium phosphide layers, which grow at much lower temperature than gallium arsenide, as every 3-5 alloys containing indium, of which thermodynamics requires lower process temperatures. So the point is to have a high growth rate for gallium arsenide, even at 650 degrees Celsius. And this can be done with uncracked arsine because the activation energy of the chemical reaction involving uncracked arsine is some 20 times lower than the activation energy when involving ACE4 molecules. As a matter of fact, arsine decomposes more easily and fastly than ACE2 or ACE4 molecules on the substrate surface. So it means that you can have equivalent growth rates, but at lower process temperatures. So it results in heterostructures grown in very short process time, so reducing cost manufacturers of such photovoltaic devices, and enough for them to become one day competitive for larger markets. Of course, when it comes to very high growth rate, an issue is the incorporation of defects, and especially deep level defects, and namely the arsenic antisite defect, usually known as EL2. And Quetsch's groups demonstrated that performance of the devices was not affected, even when the heterostructure is grown at some 300 microns per hour. Another way to reduce manufacturing costs of III-V photovoltaic devices is to move to cheaper silicon substrate and to benefit from larger wafer size, but also to grow less material in volume, namely to grow nanowise, even if Anna von Kuberta showed yesterday that maybe the math was not necessarily as good as expected. And for nanowise to take advantage of physical properties, which can be modulated as a function of the geometry, surface to volume ratio of the nanowise, and also spacing between nanowise when they are arranged in periodic arrays, as depicted yesterday or in his review papers by Ray Lapierre. So let us move to nanowire growth. Everyone knows, I guess, this results. The fast growth property of HPPE is maintained for gold-assisted vapor liquid solid growth of nanowires, here for gallium arsenide nanowires. They are grown at temperature higher than usual VLS growth as set up in MOVP and MB. Well, here HPPE opens the way to a very long nanowires grown in short time processes, maybe for sensor applications, for instance. The main properties of these nanowires is that they are defect-free all along the length of the nanowires, and then they remain cubic even for small diameters when they are supposed to experience polytypism. This was explained by Vladimir Dubrovsky and Frank Glass by comparing the chemical potential of gallium arsenide in the liquid droplet and the critical chemical potential for nucleation at the triple phase line, which is supposed to give the third side phase, and at the center, which gives the Zeimbling phase. So as you can see, once the gallium concentration in the droplet is 60%, the cubic phase should be dominant. So the high actual rates in HPPE comes because we send high input of materials, high gallium input. So the consequence is that the droplets are gallium rich. We have a high concentration of gallium in the droplets. Then the high gallium supersaturation in the droplet decreases the surface energy. That suppresses the TPL nucleation, and no first side phase can be observed, whatever the radius of the nanowire is. One of the major interests of nanowires is the possibility to grow on silicon, as the lattice mismatch strain is relieved by elastic relaxation at the nanowire surfaces. And the goal is not only to reduce the global cost of devices, but also to achieve the successful monolithic integration of III-V photonic structures and functions with silicon circuits. So when it comes to that matter, MB performs very well. And here with the pioneer work of Anna von Kuberta and then all the consecutive successes. But it's not the case for VPE processes, because they use complex chemical precursors, not gallium and arsenic beams directly. And these chemical precursors interact with the silicon substrate, and unfortunately not in the appropriate way. As a matter of fact, MOVP needs a gallium arsenide buffer layer to circumvent the issue of the melt-back etching of silicon with the organometallic precursors. And if you grow directly on silicon, obviously you have problem with nucleation, as you can see here with the very low density of grown nanowires. Well, these nucleation problems we don't really have in HVP if we use gold to catalyze VLS growth, here of gallium arsenide nanowires. But nucleation that we do have, if we try to implement nucleation problems, I mean, that we do have if we try to implement gallium catalyzed VLS growth. So in the first case, we observe uncontrolled growth with a high density of nanowires, because here growth was carried out on unpatterned and native oxide on silicon or bare silicon surface. I don't remember exactly. And in the second case here, a bad preparation of the silicon surface lead to very few nanowires due to nucleation issues. As a matter of fact, the formation of liquid gallium droplets from a gallium chloride vapor phase is not thermodynamically favorable. And we believed by that time that if we had to submit the silicon surface to a pre-treatment under gallium chloride atmosphere or mixed arsine gallium chloride atmosphere at low temperature, hoping some liquid gallium droplets would be stabilized on the substrate surface, but that obviously doesn't work. The mistake was corrected later, as you will see. Nevertheless, these poor results were still exploited, and we used these results to solve some issues encountered in MBO-VPE and MBE. And to go further in the understanding of what happens when growing on the silicon substrate, one should question the presence of silicon atoms in the catalyst droplets. So for that, let's go back to gold-assisted VLS to get a high density of nanowires. So nucleation is easier, or seems to be easier, with droplets containing gold. We have shown that there is silicon atoms in the catalyst droplet coming from the substrate. And of course, there is more silicon when growth is carried out on cleaned substrates rather than substrate with their native oxide or partially masked substrates. So Vladimir Dubrovsky and Hadi Hijazi calculated the chemical potentials involved in the catalyst droplets. And they show that adding silicon to these droplets had a drastic effect on the nucleation of gallium arsenide nanowires. And these curves must be read like this. If F is negative, which occurs, as you can see here, for high gallium concentrations, then the chemical potential in the droplet with silicon is lower than without silicon. It means that adding silicon to gallium-rich gold gallium droplets makes the initial nucleation of gallium arsenide nanowires more difficult. And of course, pure gallium-assisted growth, when the concentration is close to 1, is the most sensitive to the presence of silicon. So we can see here that silicon suppresses nucleation as long as the droplets are gallium rich and as long as a critical concentration is not reached. So as more silicon atom enters the droplets in MOVP and HVPE because of the enhanced silicon etching by the chemical precursors, we can now explain the known issue of gallium catalyzed growth of gallium arsenide nanowires by the VPE techniques. And for HVPE, VLS growth always occurs from gallium-rich droplets because of the high material input of gallium. So it means that we need an oxide layer to prevent the silicon diffusion into the droplets, then helping to start the nanowire growth. Then what about silicon when it is introduced on purpose for end doping? We know that it gives end doping for planar growth, but it seems to give p-type doping for usual VLS and PE growth of nanowires. So here again, HVP helps in understanding the behavior because it brings to the table arsenic rich catalyst droplets. And the conclusion is that it will depend on the AS of a gallium ratio in the droplet. As a matter of fact, thermodynamic calculations of the fraction of silicon atoms replacing gallium or arsenic in the crystal show that for low concentration of arsenic in the droplet, which is the case in MBE, silicon atoms replace arsenic in gallium arsenide rather than gallium, just because as the droplet contains very few arsenic atoms, it enhances the reverse transfer from solid to liquid, which is not the case for stoichiometric vapor solid growth. And HVPE, which provides the highest arsenic concentration in the catalyst droplet, for HVPE, this results in usual N-type doping by replacement of the gallium atoms. Finally, the solution was found to grow 3,5 nanowires on silicon by HVPE without gold. The idea was, in fact, to prepare the silicon surface, not with a gallium chloride or indium chloride atmosphere at low temperature, because that doesn't work, but to saturate the silicon surface with arsenic atoms under arsenic atmosphere, which will facilitate the further nucleation of the 3,5. So when it is performed on pattern substrates, you can get ordered arrays with various lengths, aspect ratios for various pitches in short time process by taking advantage of the crystal growth anisotropy of the 3,5, here for indium arsenide and here for gallium arsenide nanowires. You will have more details about these arrays of indium arsenide and gallium arsenide nanowires and silicon this afternoon with the talk of Gabin Grégoire. You can switch to planar growth here of, let's say, platelets, as you can see here, or here for gallium arsenide by changing the growth temperature or the composition of the vapor phase. And this brings us, let's say, back to the monolithic integration of 3,5 compounds in silicon. And this question was quite elegantly addressed 25 years ago with conformal growth, where gallium arsenide grows laterally from gallium arsenide seeds under a dielectric cupping layer. The seed, which was directly grown in silicon, is of course highly defective, as you can see here on the photoluminescence picture, and no misfit dislocations are created during the lateral homoepitaxy of gallium arsenide, because the seed dislocations here, of course, they can glide into the lateral conformal layer, but on a reduced area, because they are blocked by the surface of the substrate and by the capping layer. And this is evidenced or revealed by the luminescence of the conformal gallium arsenide layer here, of which front plan is shown here. The efficiency of this refining effect is again demonstrated with the conformal heteroepitaxy of indium phosphide from gallium arsenide seeds, where you can see that after the zone where the seed dislocations glide into indium phosphide, then you have a defect-free indium phosphide stripe on silicon. And as a final demonstration, you have here a complete gallium arsenide LED grown on 30 microns wide gallium arsenide conformal layer near the CMOS driver circuit on silicon. So recently, IBM and S2 Pascal worked again on the idea of growing inside cavities from gallium arsenide seeds to obtain gallium arsenide buffer layers and sufficient crystal quality after coalescence on silicon. Growth inside cavities is also studied by MBE, MOVP, so including regrowth from seeds from which expansion of nano or microcrystals proceed, and on all kinds of substrates, like graphene, as very impressively demonstrated yesterday by Jean-Christophe Armand. And here for silicon, the objective is to move to the 001 orientation, of course. So let us finish with the issue related to the growth of ternary nanowires, and especially those containing indium, whether they are nitride or arsenide. So this is an example of vapor solid selective area growth for indium nitride nanorods, showing that pure indium nitride binary materials can be grown by HVPE, but using a very specific chloride molecule, not indium chloride, but indium-free chloride. And it is also possible to circumvent the miscibility gap in indium gallium nitride nanowires, here grown by VLS. And that was demonstrated by our group and the group of Pidong Yang in the USA. And in the case of VLS HVPE, we suppose that this is due to pure atomistic growth that does not need macroscopic nucleation. I mean, that doesn't need to have the formation of a reservoir, so it avoids the reservoir effect. For gallium arsenide, gallium indium arsenide, you will have the answer with the talk of Gabin Grégoire at 2 p.m. This afternoon. So as a conclusion, I just want to say that HVPE is just a complementary growth technique to MBE and MOVPE. And I believe that the combination of the three techniques can open up imagination to design new devices for new functionalities involving micro or nanostructures in 3 dimensions. So I thank you for your attention.
Thank you very much, Evelyn, for this inspiring talk. So, we are all glad to know, I think, that finally the growth of gallium arsenide nanowires on silicon by HVPE became possible. Yeah. But my question is about this selective area grown gallium arsenide nanowires that you showed. So I think they are quite large in diameter. Yeah, can you please show them?
Yes.
Somewhere.
Here.
Yeah, here.
Yeah.
So is it critical, or it's just this sample and you can actually reduce the diameter by making the pinhole smaller?
Yes, you can use pinhole smaller, but you also have to control the ratio between the axial extension and lateral radial extension.
Mm-hmm.
So as you can see here with this curve, the radial growth can be quite, well, not, I should say, not large with respect to the axial, but radial growth still exists.
Yeah, but it's always the case, I think, in selective area grown nanowires. It's always the case. Yeah, it's normal. It's normal.
But
for the pitch, have you tried different pitches as well?
You will have to ask to Grégoire this afternoon exactly to know exactly all the pitches that are used. But yes, we had several pitches on the micrometer scale, and I don't remember if you had some substrates available with smallest pitch, but the pitch is not an issue in HVPE because there is no absorption of the growth precursors on the dielectric mask, so we are not submitted to any diffusion between.
It's perfect selectivity.
So yes, it's perfect selective growth due to the anisotropy, the growth anisotropy of crystals.
Thank you very much. Any other questions? Alexei, please. Yes.
Dr. Gil, thank you for your interesting talk. I would like to ask about growth of nanowires on silicon. You said that silicon provides N-type doping in HVPE. So in this case, am I correct that the nanowire doping level automatically should decrease with the height of the nanowire just because depletion of the droplet by silicon?
Sorry, can you repeat the question?
Am I correct that in growth of HVP on silicon, nanowire doping level automatically should decrease with height of nanowire just because of silicon depletion of the droplet during the growth?
No, because when you want to dope with silicon the nanowires, we have a rich vapor phase which contains a lot of silicon atoms with silicon gas. So the silicon atoms coming from the vapor phase,
It's in vapor. Yeah.
yes,
Okay,
it's much larger than the silicon that you can have in the droplets because of the effect of substrate. So the main input is from the vapor phase, which is completely controlled.
Mm-hmm.
So you don't have any decrease of the doping level as long when the nanowires grow.
Mm-hmm. Okay, I understand. Thank you.
I don't see any further questions, so let's thank Evelyn again. Thank you very much.
Thank you very much.
The last invited talk of the workshop will be given by Ivan Mukhin. Hello, Ivan. I don't think I have the final title of your talk, so would you please announce yourself here? We can see your slides, okay? No, we don't hear you. We don't hear you.
Micro is cut. Micro.
Hello?
Can you see me right now?
Yes, we can hear you, we can see you, and we can see your slides, so you can just start.
Thank you very much. Hello, hello everyone. My name is Ivan Mukhin. I'm from Alfred University as well, Peter the Great Academic University, and it's my great pleasure to be there today. At the beginning, I would like to thank the organizer for kind invitation to make oral presentation on that workshop, and my talk will be devoted to light emission under STM chip enhanced by metal and older-electric nanoantennas. As you can see, my subject matter doesn't relate to nanowires, but directly connected with electrically driven nanoantennas. This work was done in collaboration with ITMO University. So I just want to use was a point. So the motivation, it's well known that radio and microwaves can be generated by current oscillating within an antennas driven by high frequency voltage source. At the same time, conventionally optical antennas, which is very popular for the last decade, operate in the regime light in, light out. So to excite optical antennas, you need to use external light source. But however, for on-chip application, the electrically driven compact light source are strongly required. Currently, conventional Fabry-Perot laser or microdisc and micro-ring laser supporting with Pellegrini mode are available on the market. However, they dimensions exceeding the dimensions of resonator, exceeding the emitted wavelengths. And to the best of my knowledge, the best result, the minimal resonator size is about 1 micron, so exceeding the wavelengths of emission. And for electrically driven nanosource of photons or surface plasma polaritons are required for at least both direction. One of them is highly integrable on-chip nanoscopic transduction for conversion of electrical to optical signal, and for example for nanoscopic source of light for spectroscopy and sensing. For our work is devoted to fabrication of source of light. There's extremely low dimension up to several nanometers. It's well-known process in elastic electron tunneling in metal insulated metal structure, which allows light generation under external voltage. So the pioneering work was published more than 45 years ago, made by Lambie and McCarthy, and they have shown that if you have two crossed metal stripe divided by a thin layer of oxide, and if you applied external voltage to the structure, you can observe light emitting. The probability of this process is quite low. Normally, it requires 10,000 electrons to generate one photons, and this process was described in the term of inelastic and electron tunneling. So this is band gap energy, energy band gap of tunnel gap, tunnel contact. So there's one contact, one metal, another metal, and oxide layer between them. So during the tunneling process, there are elastic tunneling electrons which conserve the energy during the tunneling process. And the second way is inelastic process. Electron lose part of the energy during tunneling, and this energy excite gap plasmon mode in tunnel gap, which can decay radiatively and produce photons or launches PP surface plasmon polariton waves. As was shown lately, this structure, so this cross section of our crossed stripes. So there is one electrode, silver, for example, and another one aluminum, and aluminum oxide thin layer between them. And if we place this modeling result, if we placed point optical dipole in the gap, it's clearly shown that mainly surface plasmon modes localized between metal can be launched. So it means that if you'd like to observe optical photos in far field, you need some scatter centers because SPP waves is non-radiative, and you need to add some roughness or need some antennas in vicinity between metals on the top layer. Yeah, and this process was described a little bit later. So again, the energy diagram. So it could be elastic process, number 2, and inelastic process, during inelastic process or decay of energy of elastic process, we can excite optical plasmon mode in tunnel gap, which can then decay radiatively and emit light. So in the literature, different mechanisms are described. The first one exhibit a cutoff energy. It means that energy of emitted light is limited by the energy of tunneling electrons. However, the above threshold light emission is also observed and theoretically and experimentally studied. In my talk, I will be focused on this part of talk, this mechanism, since it's more effective compared to multi-electron system. So just a few formalism. So we need to excite optical modes, and electron tunneling analytically can excite this mode, and there is a probability of
Hello. Ivan, something happened.
Connection was lost.
Yes, I think his connection was lost. Mine is working.
His connection.
Yours as well.
Yeah.
Yeah, his connection.
Yeah, Ivan, I think it's a problem with your connection. So can you restart?
Yeah, can you see and hear right now me?
Yeah, it's okay. Yes, we can see you, we can hear you. Yes.
Okay, what about my presentation? Okay, can you see my slides?
Not yet. We'll see.
Pardon?
Yes,
Okay, so
it works.
sorry.
Yeah. So you just continue. Yeah, no problem.
Thanks. Sorry for long internet connection. So maybe I skip some parts. So what is important that the rate of mode excitation for any given optical mode energy is directly proportional to the local density of states of system as well as of local density of electron states of system. So the first process to excite local plasmon internal gap. Then these modes can decay radiatively or non-radiatively. So this is simple expression. So the emitted power spectrum of antenna is proportional to the quantum system and efficiency of decay of excited localized gap plasmon. So if you would like to, again, the efficiency is quite low. So there are two possibilities to increase the efficiency of this process. Firstly, we can play with the second term to improve the radiative decay of excited plasmon. So this is a very nice paper published several years ago. They have shown the group led by Professor Griffier. They have shown that if this tunnel gap considered as a sphere and metal substrate, and they introduce gold nano antenna in the shape of nanodisk in the vicinity of this gap, and they have shown that you can increase up to from 2 to 3 order of magnitude enhancement in efficiency. And what is also important, by tuning the dimension, the height or diameter of your antenna, you can tune this optical spectral emission, spectral position of emitted light. So, also, there are very nice experimental work shown that such type of antenna can perfectly work. So this is optical nano antenna, and here you can see small nanoparticles and tunnel gap organized via this elegant shape of these particles. So the thickness about several nanometer, like shown here, and you can clearly see that such structure can emit light visible by light even more, or collected with this objective. And group of Berkecht show that if you change the applied voltage, you can increase the efficiency of light emitting. Moreover, you can tune the wavelengths of maximum emission. And very classical Yagi-Uda antennas, very known in radio frequency story, was also applied for this type of antenna. And here you can clearly see that there is a possibility to tune the directivity of this of light emissions. So this theoretical and experimental works shown the perspective of use such light source electrically driven for on-chip integration. The most simple way to organize tunnel gap, and you remember that dimension, the width of this gap is about 1 nanometer. So the most easiest way to use scanning tunnel microscope, and inelastic electron tunneling has been revived when it was observed that STM tip can emit light with significant improvement efficiency. how it works. If you consider metal substrate and STM tip due to charge distribution, there is the second, the mirror of tip. So the system is equivalent to two metal tip, which actually is bow tie antenna, conventional optical bow tie antenna. This type of antenna has extremely increasing helps, which can help the inelastic electron tunneling, plasma mode excitation, and optical emission. So in the case of local contact, the probability of transition could be significantly enhanced. And now I move to the second part of my talk after the presentation of topic. So this part of talk is devoted to our experimental result. So we start with study light emission under STM tip. For convenience, we start with ambient condition. So this type of emission can be realized with STM not only in high vacuum condition, but at ambient condition. It's well known that at air, all surfaces are covered with very thin layer of water. It means that in tunnel contact between STM and metal, there is a menisque, water menisque, covering metal tip. And if you'd like to achieve emission in visible spectral range, you need to apply voltage exceeding about 2 volts. It means that you have ionic or Faraday current associated with dissociation of H2O water molecules. So in this system, at ambient condition, you have two sources of current. This is tunnel current and ionic current, and unfortunately you can't distinguish them in experiment. And as it was shown in this experimental work, if you have stable contact between STM and substrate, the emission is very low. If you start to oscillate, it's possible to increase, like it's shown here. Here you can see the Z position. It means that tip oscillate relatively to substrate, and you can emit, you can increase light emission significantly. So you can. This is our results. So this optical signal. So we use. Sorry, I forgot to mention that we use optical microscope combined, inverted optical microscope combined with STM, and as a substrate there is semi-transparent glass substrate covered with thin metal layer, and we have objective under substrate, and we're able to collect transmitted photons from the semi-transparent metal layer. And you clearly see that if we have tunnel oscillating contact, we have very nice optical signal. So we have started to, the first question was raised, how the morphology of metal film influence on the emission of light, on the efficiency of inelastic tunneling properties at ambient condition installation regime. So we have 5 different substrates covered with different thermally evaporated with different technological parameters, and the thickness of this structure was estimated through the optical experiment. So we have transmitted experiment, plane wave, and estimate the thickness. Estimate the thickness of evaporated film, and we use chromium layer to increase the adhesion of gold layer to substrate. And do you remember in my previous part, I mentioned that actually we don't have plane wave. Tunnel current can be suggested as a single point optical dipole located under STM tip. So is it correct to use this experimental result to describe a real situation? To answer on that question, we have made numerical modulation. We positioned point optical dipole under thin film and collect transmitted light. And you can see that quantitatively these results with very nice correlation. So the answer is positive. Yes, we can use a simple method to estimate, to compare the signal from different layer. And if you have a look at this column, this is normalized on thickness, on transparency of our film. This is normalized intensity of emitted light. And here you can clearly see that we have 4 order of magnitudes difference in optical signals. In that case, it's emitted lights under STM tip under external voltage. What is more important, look at the sample number 3, sample number 5. The thickness in gold is about 1 nanometer, and in chrome only 1 nanometer. So the thickness is very same. But in the same time, the efficiency varied in more than 30. How it can be explained? And to answer on that, we have studied the morphology of our film and have shown that actually our film is not continuous flat substrate, continuous flat film, but made of coalescent grains. And these grains can be described by diameter and height. And you can clearly see that you increase diameter grain, this column. Or if you decrease the height of the grain, you can modify the efficiency significantly. And in limit case of single crystal, this absolutely flat substrate, we use single crystal substrate. In that case, diameter grain is infinity and height of grain is close to 0. In that case, we can increase the emission up to 1 order of magnitude more. So how it can be explained? If we look at the quite old theoretical work made by Krylov and Robert Suris, they have shown that in STM contact or in tunnel contact, the roughness has very crucial way. They describe the probability to electrons to tunnel to the other electrodes as the effective contact area. And they have shown that if we have flat interface, in that case, the effective area increased and more electrons can tunnel to the other contacts. It can be shown by this simple image. We consider surfaces different grain size, and it's clearly seen if you decrease the height of your grain, you increase the effective area the electron can tunnel. In the same way, if you increase the height, increase the diameter of your grain, you have the same station. So this simple experiment show that in order to increase the efficiency of light emission, you need to make your substrate as flat as possible. It's quite contradictory to the first experiments of flat crossed substrate, flat crossed stripes. Do you remember? In that case, the SPP wave was excited, was launched, and you need some roughness to to convert it in far field photons. In the case of STM, it's direct process of conversion in process. So in its first part of work, we play this term. We try to increase the efficiency of SPP, the efficiency of plasma gap excitation, and we have to test tunnel current. The second part of talk devoted to STM study of IV curves. So to estimate the quantum efficiency of process from the optical experiments, you need to collect all photons and all plasmons punched in the system, and you have to take into account the effect of plasma damping and Kaplan efficiency. So you collect just part of your generated photons. But if you study IV curves, they already contain information about all inelastic process. You don't need actually to collect directly photons. You need to study IV curves. So we have modified our system. We use ultra high vacuum STM chamber combined with optical setup, align photon generated photon collection, and here the idea is can be expressed by the band diagram. If you have tunnel contact and you have enhanced optical
Ivan, the connection is lost again.
Sorry again for that. Can you see my screen now?
Yeah, it's okay.
Yeah. Sorry again for long.
No problem. You just continue.
Yeah. So we have prepared island gold. This very flat substrate is actually atomic steps. And what we have done, we measure IV curves between these center of this grain and our stem tip. In that case, due to UHV condition, we don't need to oscillate. The contact was very stable. And we have studied IV curves for positive applied voltage and negative applied voltage. Firstly, what we have consider that we have change of slope of IV curves around 1 volt. This change can be described by simplified CMOS model. Close to 1 volt transition from rectangle to trapezium shape of potential barrier curves. So it's very well known fact. Okay, but we have some features on 8 volts. These features are more pronounced when we study the second generation of tunnel current on voltage. So the simple question can arise: these features, how can be explained? Does it correspond to electron density of states, or it's related to inelastic process? If we have a look at local density of electron states of gold, you can see that we have some features in LDS near 2 volts from Fermi level. It means that this feature can be associated with a stupid process that we have increased electron states, no optical states. But you can see that above Fermi levels we don't have any features. It means that we have to have these features only on one polarities. But it's clearly seen that we have both of them on positive and negative. So since it's known that in elastic tunneling process are known to yield mirror symmetric features, we can associate these features with an elastic tunneling process. To prove that, they combine our experimental setup with optical scheme and collect light simultaneously. And we change the voltage applied to our contact, and here you can clearly see that light starts to emit at the voltage of about 1.8 volts, which well correspond to the features on IV curve. So to explain this IV curve, simple model can be considered. If voltage is low, we have a trapezium shape of contact, and we have high resistivity of our contact. When we at transition point, we change slope from one to another one, and when we apply enough voltage, which correspond to the level, energy level of optical states, we have we open inelastic tunneling process, and we have features on V curve. So at the conclusion of this part, in order to study optical states of system, you don't really need to collect optical photons directly. You need to study IV curves. And to move to the second part of my talk, how to improve the efficiency of this process. And we have told before that we need to add some plasmonic, some nano-antennas. In that case, we improve radiative decay of excited mode, and in the same time, the main process of inelastic electron tunneling easily compared to planar structure. So what we have done, we have fabricated the array of single gold nanodisk on the metal surface, and this is our experimental scheme. So metal disk in the shape of the metal antenna in the shape of gold nanodisk. This is our tip, and again, this is energy diagram. So we suppose that IV curve study allows to estimate the position, energy position of enhanced local density optical states. First, we have started with numerical calculation and consider the different position of a stem tip. This is stem tip in the center of our disk and at the edge of our disk. In the center, this is position number one. This is red curve. You can see that we can excite plasmon mode of an antenna, which is shown here, and wavelength is about 690 nanometer. But if we move the tip to the periphery of nanodisk, this blue curve, we can see that we excite the same mode, and also we have the another mode close to 560 nanometer. And you can see that both modes have hotspots at the edge of nanodisk. It means that the edge of nanodisk will have enhanced local density of states. So remember these two modes. Then we start experimental part of our work. So we have the same UHV steam chamber. This is this low resolution STM image and simultaneously acquired optical image associated with photon generation. And you can see that nano antenna enhance optical signal compared to metal substrates. You remember they have metal substrate and nanodisk. So we clearly can distinguish an antenna position via STM image and via optical image. Okay, so we can enhance optical signal. Good. When we improve the resolution of imaging, so this is again single nano antenna. This is STM topography, and this one is simultaneously acquired optical image associated with photon generation. And you clearly see that the periphery of this disk emit more light. To make clear this sentence, you can have a look at profile of this STM and optical map image. The red curve show nanodisk position, and blue lines show the optical signals. It's quite clear that at the edge, at the periphery of our nanodisk, we have enhanced optical emission. So these experimental results corresponds very nice to this numerical modeling. And in the end of this part of talk, I would like to present again the IV curve study of nano-antenna, and we positioned a STM tip in the center of nanodisk and at the edge of nanodisk, and measure IV curves, and look at the red one. Red one is at the edge of nanodisk, and you clearly see on the second derivation two features which correspond to about 590 and 690, which corresponds well to this numerical modeling. And in order to confirm that, we combine optical and IV curves on one graph. And here you can see when we have some features on IV curves, nano-antenna start to emit. So again, if we study IV curves, you can estimate the optical properties of your nano-antenna, of your single nano-antenna. You actually don't need to collect optical signal. You need to study process of electron tunnel. And actually, we have performed IV curve study across the diameter of nanostructure. Actually, this fingerprint, this IV curves, and the position here showing the position of nanotip. I don't want to discuss it in detail, but all puddles which can be shown on these fingerprints correspond to features in IV signal which correspond to features of local density of optical states of nano-antenna. So this results showing that we can improve the efficiency of light emission if we use plasma structure, and it's very important way to position your tunnel contact that you can also increase the efficiency of emission. And I guess a couple of minutes. The very last part of my talk. Okay, thanks. I would like to talk not about plasma material, but about all the electric material, for example, silicon, because for on-chip application, when we speak about CMOS compatible material, it's better to use silicon and antennas to organize optical source integrated on chip. Very brief discussion. We have performed theoretical modeling, and we put nano-antenna under STM tip made of silicon and gold material, and study the efficiency of launching of surface plasmon polyritones. In the case that nano-antenna, the efficiency is just about a few percent, but when we consider nano-antenna, this efficiency can be improved up to 1 order of magnitude. And what is more important, silicon material as good as plasma material, like it's shown here. And what we have known that the optical states of nano-antenna govern the efficiency of light emission, or SPP launching. So this curve showing the position of so we have two branch electrical dipole and electrical quadrupole of nano-antenna, and you can clearly see for both types of antenna, optical resonances govern the efficiency of SPP launch. So this slide showing that silicon materials is also compatible, is also applied for efficient electrically driven nanoscale source of light. And very preliminary results devoted to silicon structure. We have started this gold layer. We use mica substrate covered with gold layer and covered with silicon thin film. It's about 10 nanometer, and make tunnel contact with again this STM chip, and try to study optical signal stimulated by an elastic tunneling electrons. And we have found, sorry for that graphics, we have found that we have noise level. No happens. We don't have any optical signals. So silicon is not good for that application. But if you applied STM lithography, what is that? You have tunnel contact and you applied 10 volts for several microseconds. You have extremely high current, like a local current, which modifies the properties of your layer. And you can produce some morphology features, actually the alloy of silicon material and gold material. Like it's shown here, it's some hybrid metal, hybrid plasmonic aldoelectric nanoantenna, silicon gold nanoantenna, and you can produce it in the shape of a rayon. You can produce a single structure, and this one is optical signal. So we applied bias voltage and collect optical signal, and you can clearly see that we have optical signal in that situation. And then it's more important that emissions start not from 1.8 electron volts, like it was for metal material, for gold material, but emissions start from 1.3 electron volts. And this value corresponds to quantum efficiency of used valence photodiodes. So we believe that we can emit light in infrared spectral range. It means that we can excite optical stains in silicon, because we don't have any ER spectra in gold. This emission, light emission, corresponds to silicon. So we need to discuss, to study it in details, but the main idea is that in hybrid alloy of gold and silicon, due to an elastic tunneling process, we excite optical due to having plasmon properties. We excite nice localized gap plasmon on the same tip, the energy of which convert to photoluminescence from silicon. So these experimental results showing that most compatible material can be applied for fabrication and development of electrically driven nanoscale optical source. And the last part, the last slide, just a few slides, this hybrid gold silicon nanoantenna also can emit light, demonstrate very broad photoluminescence spectrum under femtolized irradiation. This is experimental spectral. You can see that we have extremely broad PL signal associated to transition hot electrons and holes from gold to silicon and their recombination. And this spectral showing that we have very, very broad enhanced local density of optical states, which is very important. It's very good for efficient solar cells. Efficient optical source. So this is the conclusion of my talk. I would like to point out that morphology of thin layers of gold essential for light emission. Features on experimental IV curves, experimentally obtained IV curves, attribute to the presence of an elastic electron tunneling. And in order to study local density of states of your nanosystem, you don't need to collect light. What you really need to analyze IV curves and plasmon materials, plasma nanoantenna, as well as all the electric and hybrid silicon material can produce electrically driven nanoantennas and the efficiency electron tunnel process enhanced by optical states of the structure. Thank you very much for your attention. If you have any question, I will be happy to answer on that. Vladimir Germanovich, I'm afraid you mute your microphone.
Can you hear me now?
Yep.
Thank you very much for the nice talk. I have a question regarding the morphology of gold film. You mentioned the gold film is made of merged grains, coalesced grains. And why is it so? Is it because it starts with three-dimensional islands at the beginning, or what is the reason? Because of course, on some substances we can have more or less flat gold layers without any grains.
It's directly correlated to the method of thermal operation which we have used to fabricate this substrate. So normally thermal operation.
Is it just standard thermal operation?
It's very broad use. It's very standard approach for metal operation, for contact fabrications. It does require very sophisticated equipment. So that's why we use this approach to operate metal. But of course, we use single crystalline gold with absolutely flat interface. Yes, it's possible to fabricate such kind of structure.
Thank you. Alexei, please.
Ivan, thank you for your talk. I have a very short question. You performed experiments mainly with gold nanoantennas. Can we expect all the same effects at silver nanoantennas, but at shorter wavelengths? Or there is something specific behind using gold?
It was shown that material properties of contacts can modify the emission spectra and STM. So silver nanoantennas should also work. And I suppose that the main position of plasma mode will be governed by the size of nanoantenna, but also by material properties of. So in that case, you will shift the position of peak.
Okay, thank you.
Are there any further questions in the audience? I don't see further questions, so let's thank Ivan again, and let's thank all the speakers of the session. So, and we will start the last oral session at 2 o'clock according to the schedule. Now we have a break. Thank you very much. See you soon.